Sorry, I don't know. I had some sort of memory issue. My phone decided to stop recording. I don't know why. That's weird. I'm trying to figure that out. Something about iCloud, but I don't have it backing up to iCloud. I don't know. Okay, so hopefully it'll keep recording here. I'll talk quickly. So what did we finish talking about? I think we were just kind of finishing up there with that combined gas law. Has to be an ideal gas, so it has to be close to or above 273 Kelvin or 1 atmospheric pressure or below. And I was just talking about if you don't fully understand that stuff in terms of the concepts, just try to at least get the information into your brain, even if you sort of have to memorize it. But I think that if you could... You did 4? But have you worked for an hour?
I did 4 lessons.
Well, do some jumping jacks, take a break, and then go back to it. I would say work at least 45 minutes would be a good goal. Okay, well, I'll talk to you about it in a minute. I'm making my video, so just wait. So, you're supposed to set a timer. Okay, shh, I'm making a video. It has not been an hour because my video has not been an hour. So now we talk about Dalton's law of pressure, partial pressures. We're kind of getting towards, I think, towards the end here. What we find is that when we have 2 or more ideal gases mixed together, the total pressure of the mixture is equal to the sum of the pressures of each individual gas. So all that is saying is the pressure of the total is equal to the pressure of one plus the pressure of the other. So if I have some oxygen, nitrogen, and carbon dioxide gases all mixed together, and the pressure is like, you know, I don't know. Sorry, I'm distracted by my children screaming. 1 atmosphere. Each one of those is going to be a portion of that one. They'll all add up to being 1 atmosphere. The pressure of an ideal gas does not depend on the identity of the gas. It just depends on the quantity of the gas. So it's how much of each one is in there. So now we learn about something called... Those of you with siblings, I've never heard this around your house. Maybe you haven't. I think our kids fight a lot. I'd be curious. Take a poll, but that probably would not be helpful because then I might just find out that nobody fights as much as we do, and then I'll just be super discouraged. So, okay, so now we're going to talk about Monzo. Wolf, if you keep stealing people's money, you can probably expect that they're going to steal your stuff. So I would just keep your hands off people's money. We're going to talk about vapor pressure. So vapor pressure is like if we have water sitting in a glass and we just let it sit. That water, you've all observed that, right? That water level is going to go down. Eventually that water will just evaporate. But how does that happen? Why is it changing from a liquid to a gas if there's no boiling involved? Well, remember that those molecules are all moving around still. It's a liquid. They're still moving. And sometimes if they hit the surface with enough energy, they can escape from the liquid. And this is something that we didn't really talk about in the last unit, but part of things evaporating or becoming a liquid is that they're breaking the that pressure of the surface and getting a little bit more energy. Am I saying that right? Let me just keep talking. I'm going to try and explain something, and I think I'm going to make it more confusing. So basically, those molecules are moving, and sometimes if they hit the surface with just enough energy, they can escape from that liquid. And so there's always some vapor that just sits above the top of a sample of liquid that the molecules are escaping from. And the vapor that sits above there and exerts some pressure is called the vapor pressure. So there's the overall atmospheric pressure, but then there's the pressure of just the vapor of that liquid that is evaporating. So think about it. It depends on the chemical nature of that liquid. So water has a low vapor pressure because it doesn't evaporate very easily, but gasoline does evaporate fairly easily. It does break that surface level, energy level, and jump out of there. That's kind of a strange way to think about it. But think about it, like, I hate to throw Brooke under the bus. He didn't realize this, but like, and I suppose I didn't think it, but I knew that the consequence, but didn't think about the chemistry of it. But he had gotten some gasoline out of a gasoline container and had it sitting like in a jar or something that he was going to use it. He must have not had it covered up because we walked into the garage and we're like, why does it smell like gas so strong in here? Well, there was a lot of gas vapor. And is that dangerous? Yes, that is very dangerous because think about it. All that gasoline is flammable. Well, when it's in a container, I have to get the match to the gas to light it. But when it's in the air and there's a lot of it in the air, any kind of spark could cause that to just instantly combust, and then all of it's going to combust. So, eventually, you're on YouTube making weird faces. Nisha, I don't know whose money you've got there.
No, this is mine.
It's yours?
It's my Christmas money.
It's your Christmas money. Okay. So, gas has a very okay, stop. That vapor pressure, Nisha, stop. Okay, there's your entertainment a break. Hey guys, I need to finish this video. Children for real, stop, 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 stop.
I said hi.
Okay, you can all take a deep breath and do some jumping jacks while we have this little interruption. Okay, Nisha, I want you to stop. So anyway, the gas evaporates easy, water not as easily, so we have much more vapor pressure when that gas is evaporating. So the boiling point, and that depends on temperature too, right? If we heat that water up, obviously it's gonna evaporate more quickly. It's gonna come out of solution like what we learned about before. So the boiling point is also can be defined at the temperature at which the vapor pressure of a liquid is equal to normal atmospheric pressure. So once, that is really hard for me to visualize. I struggled when I read this before, and now with all this distraction, so we're just gonna go with that. We'll talk about it more in class, but just remember that we can define boiling temp point. I wanna find another description of that. I feel like that's a little bit hard to visualize, so I'm gonna look for some more descriptions of that. Maybe Salcon has something good, but it's the temperature at which that vapor pressure over the liquid is equal to normal atmospheric pressure. Water boils at a lower temperature at higher altitudes. You've probably heard that. Well, maybe not, but when you cook and bake and can, especially, dropping my pen, you have to boil stuff longer or cook it longer. Well, it boils at a lower temperature at higher altitudes because the atmospheric pressure is lower. So it's lower than that 760 torr or 1 atmosphere. So the temperature to heat the water to get the vapor pressure to equal to the atmospheric pressure is lower because the atmospheric pressure is lower. So water may boil, if it normally boils at 212, I don't know what it boils at, maybe 200. I don't know how big the difference is. That's important for canning because you're supposed to boil it at a certain temperature for a certain length of time. It's actually boiling at a lower temperature, so that's why you have to do it longer. So we'll apply those things. And let's see, what's this last little piece? Gases are commonly collected in the presence of water or over water. And so that water vapor actually has to be accounted for, the pressure of that, when we use Dalton's law, as we're adding up those multiple pressures that equal the total pressure. So like when we didn't do that experiment where we mixed the not carbon dioxide, that's what you get, the vinegar and water and producing that carbon dioxide and water. Some of that you put a balloon over the top and it captures those gases. We didn't do that in class. We didn't do that one in class, I don't think so. I think we just talked about it. But some of that pressure is water pressure too. So water that's evaporated, that water vapor that's sitting over that. So we do actually have to account for that too. So this is okay, so hang in there with me. I know we've talked about a lot of things and we're like right near the end. We'll leave the stoichiometry till when we do the actual experiment in class. But we're gonna give an alternative statement to Dalton's law, and this will make probably a lot more sense when we work out some problems in class. But basically we can say that, I just realized I don't think I finished the notes that I wanted to put in here. I know I did. I was working on this earlier. I was wondering if I put it away because I was distracted by the kids, but no. I just want to make sure I finished my thought here on this very last ideal gas law. Yeah, I guess I did. Okay, so, back to Dalton's law. So we can talk about something called a mole fraction, okay? This is really not hard. It just looks like a lot of weird things, but we're gonna designate that by X. We're gonna call the mole fraction X, and we're gonna say that mole fraction is equal to the number of moles of a compound over the number of moles in the mixture. So if I have something, look at an example that they give here so I can say something more specific. Let's do an easy one here. So they talk about a mixture of gases, and this is, I am going to talk about this example because I think this makes a lot more sense. Sorry, let me just show you what I wrote down. So that mole fraction equals the number of moles of a compound over the number of the moles in the mixture. So in example 11.3, they talk about a mixture of gases contains 3 moles of oxygen gas, 5 moles of nitrogen gas, and 1 mole of neon gas. What is the mole fraction of each component in the mixture? So this is not hard, guys. This is like literally just fractions, but with more like things you don't normally think about. So how many moles are there all together? If there's 3 moles of oxygen, 5 moles of nitrogen, and 1 mole of neon, there are 9 moles total, right? In the whole mixture, there are. So 9 moles is the number of moles in the entire mixture. But if I want to know the mole fraction of oxygen, of which there was 3, I just put 3 moles on top. So there's 3 moles of oxygen as part of the whole 9 moles. So it's 1/3, right, oxygen. But if I wanted to know how much nitrogen, that was 5 moles. So 5 moles of nitrogen over 9 moles. I can't reduce that one, but it's 5/9. I could make it into a percent though, right? You can see where this is going. So I could say it's a percentage of oxygen, or it's a percentage of nitrogen, or 1 mole of neon. So it's 1/9. So it was 1/3 or 3/9, and those should all add up. So 3/9 plus 1/9 plus 5/9 should add up to 9/9 if I've accounted for everything. That's all the mole fraction is. We are going to use that to figure things out, but that's all it means by itself. And then we get to something called the ideal gas law. And the ideal gas law is, this is the thing that's going to get us into stoichiometry. But again, we're not going to do all the stoichiometry right now. So let me just show you this and we'll work some examples in class. But just so you know, the ideal gas law is going to say the pressure times the volume of something is going to be equal to the number of moles times an ideal gas constant. So if something's a constant, they're going to give that to you, times temperature. So it's just a nice, big, fancy equation that looks like that. So we can see we're going to have to figure out something where we're going to have to get into moles, and we'll get to that. So I'll give an example of this one. Let's see. One thing is, okay, can I just finish? I'm like minutes from being done. So if you're not having an emergency, just hold on one second. They do tell us, this is what I forgot to write down, that the units for that mole constant, that R, are liters times atmospheres over moles times Kelvin, because it's to cancel out everything so that we get to what we are supposed to be when we're solving that. Can those change? Yes. I mean, the atmospheres could be measured in something else. Liters could be measured in a different volume, but it's basically like volume times pressure over number of moles times temperature. So they can change, but most of the time we're going to be working in liters and atmospheres in this class. So, and actually they do tell you to memorize R. It doesn't, it's a constant, so it doesn't change. I just told you it's a constant, they'll give it to you. I was thinking of freezing point depression and boiling point elevation because those change. Now, the point though is that this R, if you changed from, you know, if you weren't in liters or you weren't in atmospheres or you weren't in Kelvin, then of course this would be different, but you don't have to memorize all the different possibilities. You just have to memorize that 0.0821 liters times atmospheres over moles times Kelvin. Even really, honestly, the units aren't as important as the number, but that does help you to see if you're doing your math right. Okay, we're gonna stop there. Is everybody glad? But look, you've just gotten this mega dose of module 11. Now we're gonna go through it in class. We're gonna do the on your owns together. When you come in, I'll know if you've listened to it because you surely will have some questions. Or maybe not, you guys are pretty smart. So you can come in Monday, ask some questions. We're gonna do the on your own together. And then the following week, we'll still work on module 11, but by that time, hopefully you'll have worked on the rest of the unit. We'll answer any questions you have about that and go over them, and then we'll do a lab. I'm really hoping that adding this hour of videos frees us up to do some lab time, because honestly, listening to me talk does not have to happen in the classroom. I mean, it's a lecture. It's nice when you can stop and ask questions, but because you're just hearing it for the first time, you know, your questions I don't know. I'm a slow processor. I listen, I think about it, and then I have questions later. Some people have questions like right on the fly, and so doing it like this might annoy you a little bit, but you are welcome on the fly to type your questions in. I'll allow comments on YouTube, or you can just send them over to me. You could do it on the YouTube board. I'm gonna post this on YouTube. I love Instagram, but I'm thinking YouTube might be more useful. I also, I intended for this to be one long video, but because it's not, it doesn't really matter, but they're just easier for me to upload to YouTube than Instagram, because it's annoying to have to keep making like 10-minute videos and uploading, like, especially for something like this, like 10 different, potentially, 10 videos or something. And that wasn't that long, but trying to keep them in order and sitting there and waiting for it to load to Instagram TV is kind of tedious. So I think YouTube will be a better resource. So I will get these plugged in to Moodle so that you can see them, and send you all a message probably on Instagram so that you know that that's there. And I'll know if you listen, because I'll know if you know what I'm talking about when you come in Monday about what we're doing. Okay, that's it. Post your questions and come in Monday ready to work on your own problems. Bye, guys.